Welcome to Unit 1, Lesson 7, Representing More Sequences Practice Problems. Okay, here's a recursive definition for the sequence. So what we have here is our first term. We have our change. So now to write the sequence, you have your first term and your change. Write 10, subtract 1.5, you're at 8.5. Subtract 1.5, you're at 7. Subtract 1.5, you're at 5.5. Subtract 1.5, you're at 4. Subtract 1.5, you're at 2.5. Okay, you get the gist. Just keep subtracting 1.5. Is this sequence arithmetic, geometric, or neither? It is arithmetic because our change is minus 5. List the first 5 terms. Well, we already did that, so we put that here. So whenever you see a definition, try to work through it, and then a recursive definition, and then answer the questions. Graph the value of the term f of n as the function of the term n for at least the first 5 terms. So basically, on my x, which is my input n, and my output is f of n, which is the same as y, and n is the same as x, inputs and outputs, we're going to make n 1, 2, 3, 4, 5. And so what I'm going to do is use whole numbers for this. I'm going to use 2, 4, 6, 8, and 10. Okay, so at term 1, my output is 10. You have to remember that sequences are the output of functions. So term 1, term 2, term 3, term 4, term 5. All right, your n's are this. And so let's go ahead and plot the rest of the points. Term 2 is 8.5. It's a little bit above 8. Term 3 is at 7. So I'm halfway in between. Term 4 is at 5.5. So this is 2, 4, 6, 8, 10. 5.5 is over here. And then my last one is at 2.5. And then as you can see, arithmetic sequences make a straight line. An arithmetic sequence, as soon as you see the word arithmetic, write plus, minus. Starts at 12, 6. How do we get from 12 to 6 arithmetically? We have to subtract 6. Okay, 12 minus 6 is 6, minus 6. Okay, so write a recursive definition, k. K of 1 equals 12. K of n is the previous term minus 6 for n greater than or equal to 2. So graph the first 5 terms. 1, 2, 3, 4, 5. 1, 2, 4, 6, 8, 10, 12. Negative 2, negative 4, negative 6, negative 8, negative 10. All right. So at 1, we were at 12. So 2, 4, 6, 8, 10, 12. You should always at least mark your x-axis. So at 2, I was at 6. At 3, I'm at 0. At 4, I'm at negative 6. And at 5, I'm at negative 12. And another straight line. Okay, an arithmetic sequence. Here we go. Another arithmetic sequence begins at 11. So arithmetic means plus, minus. To get from 11 to 7, we had to subtract 4. So A of 1 equals 11. That's your first term. Your first term in your change is most important in all sequences. A of n equals the previous term, the change for n greater than or equal to 2. Sketch a graph of the first 5 terms of A. So 2, 4, 6, 8, 10, 12. 1, 2, 3, 4, 5. The first term is at 11. Then 2, 4, 6, 8. Term 2 is at 7. Term 3 is at 3. Minus 4, yeah, 11, 7. Oh, wait, this dot should be lower. That dot is at 9, not 7. The graph looked kind of funny to me. And then -1, and then -5. And again, we see another straight line. Arithmetic functions are linear. Now, explain how to use the recursive definition to find a of 100. So if you start at 11, you subtract 4 99 times. That's all you do. Okay, let's look at our next problem here. Now we get geometric. Whenever you see geometric, multiply, divide. All right, we start at 80 and then we go to 40. How do we get from 80 to 40? You multiply by 1/2 or you divide by 2. Whichever one you want to use is fine with me. So now to write the definition, g of 1 equals 80. First term is always the first term. G of any term in a sequence is the previous term, the previous output, times 1/2 for n greater than or equal to 2. To write a formal definition, you always need all of the components. Make a table of values. So I'm going to put n on top and g of n on the bottom. So 1, 2, 3, 4, 5, 6. All right. I'm sorry, this is not notability, and I can't hold it and make a straight line. So you got 80, you got 40, you got 20, you got 10, you got 5, you got 2.5. Now, how do we use the recursive definition to find g of 100? Okay, you start at 80, you multiply by 1/2 99 times. That's how you do it. Because the first term is the first term, and you only need 99 more to make 100. Okay, match each recursive definition with one of the sequences. Okay, so we start at 1. Now, look at our change. It's times 2 plus 1. All right, so 2 and 3 start at 2. So let's work through the sequence. If we start at 1, for step 2, it's 2 times the previous term, which is 1. 2 times 1 is 1, plus 1 is 3. Now we go 2 times 3, which is 6, plus 1, which is 7. 2 times 7 is 14, plus 1 is 15. And that looked like it matches with 3. So this matches with 3. All right, moving on to the next one. We start at 1. Our change is times 2. So B matches with 2. And for C, obviously, we're starting at 80 and we're multiplying by 1/2. So C matches with 1. Okay, so now let's look at number 6. For each sequence, decide whether it could be arithmetic, geometric, or neither. So to get from 25 to 5, we divide by 5 or multiply by 1/5. 25 divided by 5 is 5. 5 divided by 5 is 1. So this looks like it would be geometric. 25, 19. How do you get from 25 to 19? You subtract 6. 19 minus 6 is 13. So this is minus 6. This is an arithmetic. And so just as an aside, you can't check between 2 terms. You have to check between more than 2 terms because this might have been times some number, but it might not get to the... Remember, arithmetic sequences add or subtract the same number between each term, between every term. Geometric sequences multiply and divide the same number to every term. Be careful about that. So let's look at C. To get from 4 to 9, you plus 5. 9 plus 5 is not 16, it's plus 7. So if I do 9 divided by 4, I get 9 over 4. If I times 9 by 9 over 4, I get 81 over 4, which is not 16. 16 times 4 is 64. So this is neither. So when you get one that you're not sure about, you have to try adding and subtracting. Also, you have to try multiplying and dividing. So I divided the 9 by the 4, and then I figure if that was my factor, it should work between every term. All right, D, plus 10 makes it arithmetic. All right, how do we get from 1/2 to 3? Multiply by 6. Times 6 times 6. All right, so times 6 makes it geometric. For each sequence that is neither arithmetic nor geometric, how can you change a single number to make it arithmetic? Well, if I go from 4 to 9 to 14, I'm adding 5. Okay, so now to make it geometric, if I go from 4 to 9 by multiplying by 9 over 4, if I do 9 times 9 over 4, I get 81 over 4. Now, you could just leave it as a fraction, but if you have to put it into a decimal, I think you're going to be at 20.25. I think that's going to be the number. All right, so that's how you solve that one.